Hi, my name is Bernoulli, and I'm here to help Ashley, Paige, Chelsea, and John talk about their fluid flow project for Physics 122.
In this experiment, we assess the velocity of water flow through a large spout with an area of 5 times 10 to the negative third meters squared and 9.6 times 10 to the negative fourth meters squared. We filled the container with water to a level of 0.17 meters. The total volume of water applying pressure onto the spouts was 1.5 times 10 to the negative third meters cubed. Our setup included a container elevated above the ground with ample space for the water to drain, a motion sensor that was placed above the spout measuring the change in position of water as time passed and the water drained out.
What do you suppose the difference in drain times would be when only the difference in the area of the spout hole is changed?
Well, according to our data, we found that the small hole has a much longer drain time, with the height being the same, the pressure the same, and the acceleration was constant.
Well, what about the velocity?
Well, as you can see, our results show that as time increases, the velocity decreases, therefore it's not constant. To eventually determine the velocity out of each of these spouts, we can utilize the quadratic fit of our graphs with a position versus time function where the large A corresponds to the acceleration, the B corresponds to velocity, and C corresponds to the initial position. We plug this into the kinematic equation to find the constant acceleration, 1/2 at squared plus vt plus y. After determining the constant acceleration for each spout, we can find the velocity as a function of time based off of the set acceleration, where velocity as a function of time is equal to at plus v naught. The small a acceleration directly corresponds to the slope, large A, in the quadratic fit. Therefore, acceleration is equal to 2a. In conclusion, the drain time of fluid depends on many factors that are all related. Velocity depends on height and area. As time increases, both the height and velocity decrease. According to the continuity equation, as area increases, the velocity of the fluid must decrease. To show this, let's take a closer look.
What would happen to the drain time if the depth doubles?
Well, John, drain time increases by about 30%. We found this as using our data through the use of kinematic equations.
What happens if the spout area doubles?
Well, we found that the drain rate increases by about 80%. We found that the small hole drained at 377.75 seconds to 55.7 seconds.
What happens if the cross-sectional area doubles?
According to the flow rate equation, Q is equal to the change in volume over the change in time, we found that the drain time increases by nearly 50%.
What if both spout area and cross-sectional area doubles?
Nothing's going to happen. The time remains the same.
I don't know about you guys, but I got so excited about water and flow rate that I'm going to go splash around in some water later today.